Welcome everyone. So first I would like to make some announcements. The code for today I also wrote it here, but in case you cannot read it, is 506 780. So first of all, about the lecture. I plan to have the lecture typically starting from 4 p.m. to 5:30. So please make sure to come in time. And after that, there's still time for questions. But I think it's better if we start early so that everyone can also leave earlier. Second point, office hours. So I also announced that on Blackboard, I will hold office hours on Thursday 2 to 4. That is right before the lecture. And if you would like to come to the office hours, then please send me an email. Okay, the instructions, you can find them on Blackboard. So the idea is that this is 2 hours, so I will offer 8 15-minute slots. Okay, then exams. So I've received a lot of emails about the form of the exam. Again, at this point, I don't have the official information yet. I can only tell you what I plan to do, but there's no guarantee this will happen, so please take this with caution. So for the midterm, I plan to have an online exam that you have 1 or 2 days. I will upload a problem set, and you will have to submit it via Blackboard. And for the final, I plan to have an on-campus exam of approximately 90 minutes. And about the questions that will be asked on the exam, so if it will be an on-campus exam, I plan to have exercises that will be similar to the problem sets. So tomorrow I will upload the first problem set, then you will have an idea how the exam will look like. All right. We also have a teaching associate, Saba. He will teach some of the tutorials. I will teach others. He will also offer an office hour. The information on that you can find on Blackboard. Okay, and in general about announcements, so if you have any questions, please always check Blackboard, and please also come early to the lecture because I plan to have any announcements in the first 5 minutes of the lecture. And in case you cannot make it, there's also a recording, then just watch the first 5 minutes of that. Okay? All right. Then let us start with the second lecture. Today we will discuss choice under risk. Okay? And with that, we will first of all consider the baseline model, which is a utility theory for a riskless choice. That is for an environment where the decision maker knows the state of the world. Okay. Yes, actually it worked right now, so yes. Yeah. Thank you so much for coming. All right. So first of all, let me show you the model parameters of the model of choice in a riskless environment. Okay, we will have a finite set of outcomes, x1 to xk. We denote the set of outcomes by capital K. And we have a decision maker that wants to choose the best outcome. And the decision maker has preferences over those outcomes. Okay, we use the standard notation for that. So X is preferred towards Y. This one means that the decision maker weakly prefers X to Y, which could be either a strict preference, which is denoted like that, or a weak preference in the sense of an indifference. Okay, so between any two outcomes, there are three options. Either the decision maker weakly prefers one option, X, over another option, Y. He strictly prefers option X over option Y, or he is indifferent. Okay, and another way to think about indifference is, well, this means that the decision maker both weakly prefers X over Y, as well as weakly prefers Y over X. Okay, so let me make this note, because we might make use of this in one of the proofs later. So keep in mind that indifference is equivalent to the decision maker preferring X over Y and Y over X. Okay, and this symbol here, this means and. If you have a statement and want to say two things hold true at the same time, you use this kind of head. Okay, and what is important is here's no whisk. So when the decision maker makes a choice, he knows the outcome for sure. Okay. In choice theory, we typically assume a few axioms that make sure that the preferences we describe are rational. And in the basic model, this means that we have two axioms. The first axiom is completeness. So completeness means that for any two outcomes, X and Y, at least one of the following two statements holds true. Either the decision maker prefers X over Y, or the decision maker prefers Y over X. Okay, so completeness means that the description of preferences is complete in the sense that whenever we make a binary comparison, we can make a statement about it. We always know which of the two is preferred over the other one. We cannot say we don't know. Okay, and the second axiom is transitivity. So transitivity means that whenever we have three different outcomes, X, Y, and Z, if the decision maker prefers X over Y and he prefers Y over Z, then the decision maker should also prefer X over Z. Okay, these are standard axioms that are quite intuitive, and typically whenever we refer to preferences that satisfy both completeness and transitivity, we call such preferences rational. Okay, let me write this down. In the model with whiskless choice, we call preferences rational whenever they satisfy both axioms. Okay. Generally, so our question is, which decision should the decision maker take? And in general, we could do that based on the preference relation we just defined. But usually, it's a lot easier if we think about utility instead of preferences itself. The advantage of utility functions is that they assign a number to each outcome, and then we can compare two different outcomes based on the utility, the number that we associate with each of these outcomes. Okay, and that makes it a lot easier because in order to find an optimal outcome, we can use the standard mathematical tools, maximization, first order conditions, etc., to find the answer to our question. Okay, but for this, we actually have to make sure that we can represent our preferences by a certain utility function. Okay, let me make this a bit more formal. So, what is a utility function? A utility function is a real-valued function that assigns to each outcome in the set of outcomes x a real-valued number. So, in other words, for any x, the utility is u of x, and this is some real number, for example, 2. And a utility function that represents a certain preference relation is such that the following equivalence holds true, namely for any two outcomes x and y, whenever the decision maker prefers x over y, this is equivalent to the utility of x being higher than the utility of y. Okay, so in other words, a utility function assigns to each outcome a number in such a way that all the information about pairwise comparisons, about the preferences, are retained. Okay, so this means whenever we talk about higher utility, this means that the outcome is preferred. So in that sense, what I already mentioned 2 minutes ago, since higher utility is associated with more preferred outcomes, maximizing the utility function is nothing else than finding the most preferred outcome. Okay, so in theory, utility functions are a quite useful device. However, we have to make sure that the utility function that we associate with a certain preference relation indeed captures all this information. Okay, and this is one of the theorems that we want to show today, the so-called utility representation. We can represent any preference by a certain utility function. Okay, let me start with one preliminary result. Okay, so this is a useful result that we will need later on in order to prove the utility representation theorem. Again, basically the idea is that we can split preferences into strict and weak preferences. this might be useful because sometimes we want to talk about one outcome being weakly better than another one, or the opposite, that the other one is strictly worse than the former outcome. Okay? So this lemma states the following. If we assume the axiom of completeness, then the following two statements are equivalent. Okay, the first, that a utility function represents a certain preference relation. And second, that for any two outcomes, whenever the decision maker strictly prefers outcome X over outcome Y, the utility is strictly higher, and whenever the decision maker is indifferent, the utility function is the same. Okay, so at this point, let me say that this is not a surprising result. In fact, it is quite intuitive. We should expect that, well, if we have rational behavior, and in this case, in fact, we only need completeness, so this is important, we can prove this result without transitivity. So we don't even need fully rational preferences, only completeness is necessary. Okay, and then this statement says, first of all, it is an equivalence result. So we know that the first statement is equivalent to the second one, meaning that both, if the utility represents a preference relation, then we can do the splitting here. And second, whenever we can do the splitting, it is a preference. It is a utility representation. Okay, the first one is rather obvious because if we have typical preferences, we should assume that, well, indifference implies that the utility is the same, and also strict preference implies that the utility is strictly higher. However, the other direction is not that obvious, but indeed it follows from the definition of representation. Okay, I would recommend that you try to prove this result. Indeed, it's not that difficult, and we will also prove other results today based on which you can try it yourself. But I would really recommend that you try to prove this by yourself. Okay, and let me just give you an idea of how this proof should be structured to give you some hints. So when we want to show this, you first of all show one direction, because this is an equivalence. So you have to show that the first statement implies the second one, and separately that the second implies the first one. Okay, so you first have to show that 1 implies 2, which basically means that if you assume you have a utility function that represents a preference relation, then we can write these two things. Okay, so what you want to show is that X strictly prefer to Y implies this. And I put dots here. This is the part that you have to solve, but you can use any statements about 1 for that. So in particular, the definition of a utility function. And similarly, you have to show that if X and Y are equally preferred by the decision maker, then you end up with the same utility. Again, you can use the definition in 1 to prove this. Okay, and on the other hand, if you want to show that 2 implies 1, then you want to show that whenever you have two outcomes such that x is weakly preferred to y, this is equivalent to that. Okay, and let me give you the initial step for that. So whenever you have this one, this is equivalent to either the decision maker strictly prefers x over y, or the decision maker is indifferent. Okay, and this term here, this is kind of the switch to the end, so the end is ahead, and this one is just symmetric along the horizontal axis, so this means or. Oh, excuse me. Okay. So, as I just said, this lemma will be useful when we want to show the utility representation. So, let me show you what this means. Utility representation means that we again have an equivalence between two statements. The first statement is that the preferences are rational, that is, they satisfy completeness and transitivity. And the second statement is that the preferences are represented by some utility function. Okay, why is this theorem interesting? Well, first of all, this is a very strong statement. So we know that rational preferences, that is the two axioms, completeness and transitivity, are both necessary and sufficient to have a utility representation. So why is this useful? First of all, whenever you have a certain preference relation, if you are wondering if you can do anything about it, if you can write it with a utility, you only need to check whether the preference relation satisfies completeness and transitivity. This is rather easy. And then you know, okay, there must be some utility representation on that. And also the other direction is interesting because whenever you have a utility function that represents a preference, you indeed know that this is a rational preference. So it cannot be that you have some weird utility function and that the corresponding preference does not satisfy completeness or transitivity. Okay. So we want now to prove this statement. Okay. Let me put the theorem up here. Okay. So this statement is an equivalent statement. So like in the lemma, we proceed in 2 steps. First, we show that the second statement implies the first one, and then we show that the first statement implies the second one. Okay, so let's start with 2 implies 1. Okay. So first of all, fix any 2 outcomes x and y. Fix any x and y in the set of outcomes. Then we know that there is a certain utility associated to that by the second statement. So let's think about these 2 utilities, ux and uy. We know for sure, independent of what x and y is, that one of the following has to hold true. Either utility of x is larger than utility of y, or utility of y is larger than utility of x. Okay, we take 2 outcomes, we look at their utility, these are 2 numbers, we can always say which of the 2 numbers is higher. Okay, this statement is in other words a statement about the completeness of the space of real numbers. This is what we use to show completeness of the preference relation. Okay, so we know this. Then also we call that the first statement, ux is larger than uy. This is by statement 2. We know that the preference can be represented by utility. And let me go back to the definition of a utility. Okay, so this was the definition of a utility representation, that this statement is equivalent to this statement. So this is what we use in the second statement. The second statement is nothing else than this equivalence. Okay, so by the second statement, this is equivalent to x being preferred to y. And similarly, this statement is equivalent to y being preferred to x. Okay, but what do we have now? Well, we know that for any x and y, either u of x is larger than u of y, or the other way around. And these statements are equivalent to, well, either x is preferred over y, or y is preferred over x. So in other words, what we have now is, for any x and y, it must hold true that either u of x is larger than u of y, which means x is preferred to y, or u of y is larger than u of x, which means u of y is preferred to, y is preferred to x. Okay? And if you recall, this is exactly the definition of completeness. Okay, so completeness is satisfied. Okay, let me pause for a second and give you the opportunity to ask questions. Or if I'm too fast, then also please let me know. I'm happy to go slower or faster depending on. All right. Then let me continue. So we have shown completeness. Second, we have to show transitivity. Okay, how we do that? We call transitivity means that if we have three outcomes, x, y, and z, then x preferred to y and y preferred to z implies x preferred to z. Okay, so now we fix some x, y, and z in the set of outcomes such that x is preferred to y and y is preferred to z. And we want to show that this implies x is preferred to z. If we can show this, we have shown transitivity. Okay, but how can we do that? Well, let's start with this statement. X is preferred to y and y is preferred to z. Okay. So again, we know that statement 2 holds true. That is, the first one is equivalent to ux being larger than uy, and the second one is equivalent to uy being larger than uz. So by the second statement, this is equivalent to this. Okay, but if we know that u of x is larger than u of y, which is larger than u of z, that implies that u of x is larger than u of z. Okay? But again, by the second statement, this is equivalent to x being preferred to z. And this is exactly what we wanted to show here. Okay? So this means that transitivity also holds true. Okay, so what have we done here? With the help of the knowledge of statement 2, that is a utility representation, or this one equivalence, x preferred to y is equivalent to u of x being larger than u of y, we could derive that the preferences must be complete and transitive. And this is all what we needed to do. Okay. Any questions so far?
Is the set of outcomes going to be a finite set? Can it not be a set of real numbers?
Good point. So in general, it could be a non-finite set. So it would still be in the real numbers, but you could have, for example, an interval, like the interval from 0 to 1. This would be a continuum of real numbers. Let me think. I think for this proof you don't run into any issues, but later on we have a continuity result, And for this one, it is crucial that we assume finiteness. But that's a very good point, thank you. Okay, so typically we assume finiteness so that it becomes easier. In the literature, there are a lot of papers that try to generalize this, but for now we remain with the simple case. Any other questions? Okay. Then let us show the other direction, that the first statement implies the second statement. Or in other words, if we know that preferences are complete and transitive, we want to show that x being preferred to y is equivalent to u of x being larger than u of y. Okay? So for this proof, we need a few definitions. Let me give them first. We define a so-called lower preference set, which we call L of x. Okay? L stands for lower preference set. How is this defined? So when I define something, I usually write like an equality sign and 2 dots in front. This one means define. This is defined as the set of outcomes. Therefore, we write the brackets because we're talking about a set. The set of outcomes z in the set of outcomes x, such that x is weakly preferred to z. Okay, what does that mean? This is the set of outcomes such that the decision maker prefers x over z. That is, this is all the set of outcomes that are less preferred to x. So for example, if we had the outcomes x1 to xk, suppose they were ordered in a way that the first one is the most preferred one, second preferred, and so on. Okay, let me write this down here as an example. If we had x1 rather than preferred to x2, preferred to x3, and so on, then the lower preference set of any outcome x would be all outcomes to the right of this. Okay, so for example, L of x1, that would be actually all outcomes because this is the most preferred outcome. L of x2, well, only x1 is strictly preferred. Let me also put a strict preference here, just to be clear. So these all should be strict preferences. Lx2 would be x2, x3, and so on. Lx3 would be x3, x4, x5. Okay, so the sets shrink even more. Maybe let me give you another example. Okay, so we have x is strictly preferred to y, z is strictly preferred to y, and X is strictly preferred to Z. Okay? And can you tell me what is L of X, L of Y, and L of Z in that case? I give you 2 minutes to think a little bit about this. So X is preferred to Y, Z is preferred to Y, and X is preferred to Z. You can also think of which of the 3 is not necessary for the description due to transitivity. Okay. Does anyone want to try? So let's start with L of X. L of X is the set of outcomes that are not preferred to X. Any idea? Yes, please.
Does X itself count as well?
Yes, yes, very good point.
Z, Y.
Yes, exactly, very good. So this is one rule. If you have some L of X, X is always contained in the set. So L of Y, Y is contained, L of Z, Z is contained. And here we see that both X is preferred to Y and X is preferred to Z. So this is X, Y, and Z. What about L of Y? Perfect. Only X is strictly preferred to Y, that is, X is not in L of Y. And what about L of Z? Perfect. Okay. So we have understood. Yes, there's a question.
Well, Z was preferred to Y. You should have Y,
It's written here, Z is.
Oh, let me see. Yes, so actually it should be the other way around. It should be Y and Y of Z. Yes, thank you very much. Okay, so now we have understood what a lower preference set is. And based on that, we will define a new term, which turns out to be our utility function. Okay? So now we define the function u of x. And u of x is the absolute value of x. And we define this for any. Okay, so this means for all x in the set of outcomes. Okay, so this is the absolute value. And the absolute value of a set, L of x is a set, is defined to be the cardinality of the set or the number of elements in the set. Okay, so this is the cardinality, or number of elements in the set L of x. Okay, so the function u counts how many outcomes are less preferred to x. Okay, so the number u of x is higher, the more outcomes are less preferred to x. And as you might guess, this turns out to be our utility function. Because if an outcome is more preferred, there are more outcomes that are less preferred, so the number is higher. So this outcome should be more preferred towards one that has a smaller number, towards which less outcomes are preferred, are less preferred. Okay. So now let us show the statement. And we call, let me put the statement again. The statement was that preferences are represented by a utility. In fact, we can use the lemma that we had before, this distinction into strict preference and weak preference. Okay, let me show you this again. So we have those two statements. Now we have one, we want to show that 2 holds true. But we can use the fact that 2 is equivalent to this statement. So if we can show that this statement holds true, then by the lemma, we know that the first statement also holds true, that the utility represents a preference. Okay, so all we need to show is the second statement of the lemma. And also recall that for this, we only need completeness. And this is satisfied by the first statement, by this one, because we assume completeness. So it's perfectly fine to use the lemma. Let me write this down. Okay. So recall that preferences are complete by the first statement, so we can use the lemma. So what we want to show is the second statement of the lemma, which was A, if x is strictly preferred to y, then u of x is larger than u of y. And B, if x is equally preferred to y, then u of x is equal to u of y. Okay. So let's first of all prove part A. So suppose we have two outcomes such that x is strictly preferred to y. Then we want to show that u of x is larger than u of y. Okay. How do we do that? We want to show that the lower preference set of y is a strict subset of the lower preference set of x. Because this implies that the absolute value of L of y is strictly smaller than the absolute value of L of x, which implies that the utility of y is strictly smaller than the utility of x. Okay, so first let's show that L of x is a subset of L of y. Let's show this statement. Okay, how can we show this? We can show this by proving that whenever we have an element of L of y, let's call it Z, this element is also in the set L of x. So if we have some element in L of y, we want to show that Z is also part of L of x. But first of all, by the definition of the lower preference set, if Z is in L of y, this means that y is weakly preferred to Z. But by transitivity, we call that if we have x is preferred to y and y is weakly preferred to z, then also x is preferred to z. Okay, and if x is preferred to z, well, that means that z is in L of x. Okay, so for any element in L of y, we know that this element is also in L of x. Hence, we have shown that L of y is a subset of L of x. We want to show that the utility of x is strictly higher than the utility of y. So we have to show that indeed L of y is a strict subset. So we have to rule out that L of y is the same as L of x. Okay? But how can we do that? Well, notice that x is in L of x. Okay, we know that any element is part of its lower preference set. However, because x is directly preferred to y, x is not in L of y. X is not less preferred to y. Hence, we have found an element that is part of L of x, but not part of L of y. So L of y is a strict subset of L of x. It's not the same sets. And because L of y is a subset, this implies that L of y is a strict subset. And if L of y is a strict subset, that means that the number of elements in y is strictly smaller than the number of elements in L of x, which implies that u of y is strictly smaller than u of x. Any questions? Okay, then let us show the second direction, proof of part B. Suppose the decision maker is indifferent between x and y. Then we want to show that u of x is equal to u of y. Okay? We will show that in the following way. We will show that L of x is equal to L of y, which means their absolute values are the same, which means that the utility is the same. So in order to show that L of x is the same of L of y, we show both that L of x is a subset of L of y, as well as L of y is a subset of L of x. So we will prove these two statements. Okay? Again, we prove them by showing that all elements in L of x are also in L of y. So if we have some element in L of x, then this means that x is preferred to z. So x, which is where the decision maker is indifferent to y, this must be preferred to z. So by transitivity, this implies that y is also preferred to z, and hence z is in L of y. On the other hand, if z is in L of y, then by transitivity, we know that y is the same as x is weakly preferred to z. So x is preferred to z. So z is in L of x. Okay? So from these two statements, we can get that L of x is equal to L of y because each is a subset of the other one. Hence, also, their absolute values are the same. Hence, the utility is the same. Okay, and then with that, let me just summarize this again by the previous lemma. The second statement follows. Okay. So, do you have any questions about this? Yes. In which row?
When we say L, X, Ly
if z is an L of y. Oh. Okay. Let me also say, so I know this is a very complicated proof, but I also think that once you get into this, it becomes a lot easier. So if you practice this a lot, it's actually, you know all the tricks that you need to use, for example, this subset trick, etc. Let me also say that, for example, in an exam, I would not expect you to come up with such a proof, only that if we had such a proof, a very similar version of that. Okay, so what I would recommend you to do, if you have not understood every single part of this right now, go through this again at home. And if you have more questions, please come to my office hours or ask me after the lecture, okay? All right. So I would like to make one final remark on the model without risk. So we have talked about the fact that given the two axioms, according to our utility representation theorem, we can always find a utility function that represents our preference relations. One remark I would like to make is that typically the utility function is not unique. So there can be multiple utility functions that represent the same preference relation. But those utility functions are unique up to increasing transformations. Okay? What do I mean by that? So let me write this down. A preference relation can be represented by more than one utility function. Okay, this is because utility is ordinal. We only care for the ranking. So for example, if we have only two outcomes, x and y, x is preferred to y. We could say, okay, that's represented by a utility function where we associate value 2 to x and value 1 to y. But we could also say, well, this is also represented by a utility function where we assign value 4 to x and value 2 to y. Okay, these would be two different utility functions that represent the same preference, namely x being preferred to y. A more general example would be if we have some utility function u, then the following utility function v, which is the exponential function, these two represent the same preferences. Okay, what does this mean? V equal to e to the power of u means for any outcome x, v of x is equal to e to the power of u of x. Okay. This is just a shortcut for the description of the function v. Okay, or if we want to say that more generally, if utility function u is represented by represents this preference relation given by this, then whenever we take any increasing transformation of u, for example, we multiply everything by 2, we add a constant, we take e, the exponential function, this does not change the ranking. Okay, so mathematically this is equivalent to f of u of x larger than f of u of y if f is an increasing function. Is any strictly increasing function. Okay, so this is the idea of ordinal utility, that only the ranking or the order matters, not the absolute value. So only this inequality matters. So this is summarized in the corollary here. If preferences can be represented by a utility function u, then preferences can be equivalently represented by any utility v, if and only if v can be derived from u via a strictly increasing function f. Okay, so whenever v is equal to f of the function u. Okay. Why is this result helpful? Well, first of all, this is of theoretical interest because this shows that indeed there's not a one-to-one mapping between preferences and utility, but there can be many utility for one preference. However, they all have the same quality in the sense that they must be an increasing transformation of one another. And practically why this is interesting is that it allows us to choose an easy utility function. So for example, if we have some finite set of outcomes, we could take a very difficult utility function, for example, one that has like very small and very high values that might be difficult to compute. But actually it might be easier to take a simple structure. One example of those is the exponential function that I wrote here. A benefit of this one is that the derivative is the same. So if we were to take a first order condition, this would be relatively simple. So in that sense, it matters which utility function we take to consider our maximization problem. Okay. So, in the second part of the lecture, we want to talk about choice under risk. The model will be quite similar. The only difference is that the outcomes are not known to the decision maker, so we cannot define preferences on outcomes. But we have to find another concept that I will introduce in a minute. Okay. So now we consider the model of choice under risk, which is quite similar to before. Again, we consider a finite set of outcomes, but there's risk. The decision maker does not know the outcome, but only the probability of each outcome. Okay, so the decision maker is endowed with a probability distribution over the outcomes. So we can no longer define preferences on outcomes because the decision maker doesn't know it. Instead, we have to define preferences over those probability distributions over the set of outcomes. Okay. And for this, we will use a certain term. we call those probability distributions lotteries. Okay. There are two kinds of lotteries, simple and compound lotteries. Let us start with a simple lottery. A simple lottery is basically a probability distribution over the set of outcomes. We denote it by P, and P describes a collection of the different outcomes and the probabilities that are associated with that. Okay, so this one here, this tuple is the probability of outcome x1 and x1, and so on. This is probability of xk and xk. You might wonder, why don't we simply write down the probabilities? Okay, we could just write a list of px1, px2, px3, and so on. The reason why we don't do that is because it's not descriptive. We could have a case where all outcomes are assigned to the same probability. Like, we have two outcomes and then it's 1/2, 1/2. We have to know which is associated with which outcome. In the case of 1/2, 1/2, it doesn't matter, but suppose we had 1/2, 1/4, 1/4. Then we have to know which is the 1/2. So we always have to write down, okay, this is the probability and this is the outcome that we are talking about. Okay? Then this is a simple lottery because it goes back to the outcomes. We could also think of higher order lotteries. Okay? So a compound lottery is a probability distribution over a set of lotteries. This could be either simple lotteries or also compound lotteries. And this means that we also have a collection of probabilities, but they are assigned to different lotteries, Q1 to Qj. Okay, let me explain the difference to you. A simple lottery is in fact a special case of a compound lottery. Okay. Let's first of all think about an example of a simple lottery. And I want you to train this way of description, so I would like you to write down what would be the lottery. So the example that we study is a fair coin toss that yields £5 if the outcome is heads and £10 when the outcome is tails. Okay? So I would encourage you to write down the simple lottery of this problem. Okay. Can anyone tell me what the lottery is? Just tell me the numbers that, like in a row. Yes, perfect. So it is 1/2, and the outcome is 5, and 1/2 with outcome 10. Okay. This is a simple lottery. You could also write this down in a diagram. Okay, so you could say, okay, we have two different options, £5 and £10, and we have the associated probabilities 1/2, 1/2. Okay, or more generally, by the way, if you can't see anything, then please let me know. I sometimes don't realize when it's too low, okay? Okay, more generally, we could think of this as we write the different outcomes at the end, and not on each branch of this tree, we write the corresponding probabilities. And an example of a compound lottery would be, so Q1 could be a lottery over two outcomes, and Q2 could be a lottery over other two outcomes. So X1, X2 for Q1, X3, X4 for Q2. So what a compound lottery would be, where we have P of Q1, P of Q2, here are the two lotteries, and each lottery is a lottery in itself. So this has the outcomes X1 and X2 with probabilities Q1, X1 and Q1, X2. This is Q2 is a lottery with outcomes X3 and X4 with corresponding probabilities Q2, X3 and Q2, X4. Okay, and a simple lottery is a special case of a compound lottery. Yeah, because we could always think of the lottery Q as just yielding one outcome with probability 1. Okay, so a simple lottery is a special case of a compound lottery. Okay. Do you have any questions? Okay. So we now have a slightly different model. Before we had a set of outcomes X, and we were defining a preference relation on the set of outcomes. Now we have a set of lotteries, which we denote by L, and we define a preference relation over the set of lotteries. Okay, so this preference relation is defined whenever we have two different lotteries, P and Q, in the set of lotteries, then P is preferred to Q whenever the utility of P is is higher than the utility of Q. Okay. We could now think, well, let's just assume the same axioms and derive the same results that we had in the Wiss-Glass model. And in fact, we also require completeness and transitivity here, but we need more. If we only assume completeness and transitivity, we can still have irrational behavior. An example of this are so-called Dutch books. since I don't have that much time anymore, I would skip this example. I will upload a note on that, and you can read about this, okay? Basically, this example shows that this allows for irrational behavior, that you could say, well, a consumer might prefer one outcome over another one, but might not prefer a lottery over outcomes over the original one. And such behavior would be possible with complete and transitive preferences, but it would be in some sense irrational, because we could, by transitivity, get that actually one lottery is strictly preferred to itself, which is not possible, or which we don't want to allow. Okay? So we need a more thorough definition, and this definition will be the expected utility. So the expected utility, typically we will call such a function capital U. So expected utility, we typically write it as capital U, of a lottery is defined as follows. So it is a function U of P, which we also write down as expected utility of P, EUP, which is simply the sum over the expected utilities. So we sum the utilities weighted by the probabilities. Okay, so this is K. We sum over all possible outcomes. And we also see here this small u. This is the so-called von Neumann-Morgenstern utility function. This is the utility function we had before, defined over the set of outcomes. Expected utility is defined over the probability distribution of those outcomes. But we need a certain underlying von Neumann-Morgenstern utility to describe the expected utility, capital U. And similarly, we can define expected utility for compound lotteries. This here was for simple lotteries. For compound lotteries, expected utility is the sum over weighted expected utilities weighted by the probability of the corresponding lottery, QI. Okay? So expected utility is simply taking the average, and we call a decision maker an expected utility maximizer if we have the following equivalence. Whenever the decision maker prefers lottery P over Q, the expected utility is higher than the expected utility for Q. Okay. Then let me also make one remark on risk attitudes. So we know that the utility function, the von Neumann-Morgenstern utility function, shapes our expected utility. And in fact, the shape of the von Neumann-Morgenstern utility function tells us something about the risk attitude of the decision maker. So typically we consider risk-averse decision makers. So a decision maker is risk-averse if, for all lotteries, the decision maker prefers the expected value of the lottery over the lottery itself. So he does not want to have the uncertainty, but he prefers to get the average of them. Okay. In other words, you can write this down So an expected utility maximizer is risk-averse if we have this inequality here. This is simply plugging in expected utility into the representation theory. And by Jensen's inequality, you can show that indeed this means that the utility function is concave. Okay, why is that? So let me briefly write down Jensen's inequality. For some function v, that means that the function v at the convex combination of the points x and y, weighted by lambda and 1 minus lambda, where lambda is between 0 and 1. This is larger than lambda v of x plus 1 minus lambda v of y. If that holds true for any x and y, then this function v must be concave. Okay? Suppose this is our function v. These are our points x and y. So this is v of x. This is v of y. Here we would have the point y lambda x plus 1 minus lambda y. This term here is this point. But this term here is this point. So this is smaller. And there you see, whenever we have this inequality, we must have a concave function that is above the line. Okay. So risk aversion will be the kind of risk amplitude that we will see most often. There are also two other. One is risk neutrality. So instead of risk averse, we have risk neutral. This does not change the definition a lot, except that the agent is risk neutral if it's indifferent between the lottery P and the expected value of the lottery. In that case, we would have equality here, and the function u would be linear. The third kind is risk-seeking behavior. In that case, the decision maker strictly prefers or weakly prefers the lottery over the expected value of the lottery. So here we have a weak inequality, and this means that the von Neumann-Morgenstern utility function is convex. Okay.
Sorry.
Of course. So next I briefly wanted to talk about ordinal and cardinal utility again. Like in the baseline model without risk, we would like to think about expected utility as ordinal utility. However, this does not mean the same for the von Neumann-Morgenstern utility function. Okay? So, what do I mean by that? We typically want that expected utility is ordinal, that is, it is unique up to increasing transformations. But what does that mean for the von Neumann-Morgenstern utility function? Typically, the von Neumann-Morgenstern utility function has to be cardinal so that the expected utility is ordinal. And cardinal means that it is unique up to positive affine transformations. What is a positive affine transformation? So an increasing transformation is whenever we can write, we have expected utility is equal to f of expected utility of the function u, where f is an increasing function. A positive affine transformation of the von Neumann-Morgenstern utility function would be that v is equal to a times u plus b, where a is positive and b is some constant that can be positive or negative. Okay, again, in the notes that I will upload, you will find examples that show that if the von Neumann-Morgenstern utility function is not cardinal, we might not end up with ordinal expected utility. Okay? So the statement you should keep in mind is the following: uniqueness of von Neumann-Morgenstern utilities. Basically, it says that a utility function is ordinal, or two utility functions, expected utility, are ordinally equivalent whenever the von Neumann-Morgenstern utility functions are cardinally equivalent. Okay, so this result is helpful because now we know, okay, when we are looking for an appropriate expected utility and we want to change it a little bit because we know we can do increasing transformations of the expected utility, we should make the transformation in a way that the von Neumann-Morgenstern utility is a positive affine transformation. Okay. And finally, I would like to show you the equivalent result of utility representation in the Whiskey model. And for that, we need 4 axioms. Okay? These so-called axioms of expected utility. Okay? So the first one is the so-called mixture monotonicity axiom, which means that if we compare 2 lotteries with the same possible outcomes, the outcomes are P and Q respectively, then we prefer lottery 1, this one, over lottery 2, if and only if we associate higher probability to the more preferred outcome. In that case, P is preferred to Q, and therefore we prefer 1, this one, over 2, because R of P, the probability here, is larger than the probability here. Okay, so mixture monotonicity means that if we compare lotteries with the same 2 possible outcomes, P and Q, the lottery that assigns higher probability to the more preferred outcome is the preferred lottery. Okay. The second axiom is the so-called reduction axiom. This one basically says, we had this example before where I showed you how a compound lottery basically reduces into a lottery over outcomes if we take 2 steps. Okay, So we might look at the case where we have here P is a lottery over lotteries, and we can just compute the new outcomes, the probability of the initial outcomes, by multiplying the probabilities of the respective lotteries in this way. And then we get P hat, which is a lottery over final outcomes. And this axiom tells us, because we are only interested in final outcomes, the von Neumann-Morgenstern utility only depends on final outcomes, and we have expected utility. Well, in that case, it should not matter whether we consider compound lottery, lottery over lotteries, or the same equivalent just over outcomes. The third axiom is the so-called substitution axiom. This basically says if we have an arbitrary lottery and we replace one outcome by an equivalent outcome, which the decision maker is indifferent between, then the decision maker is also indifferent between those two lotteries. So in this example, we have the outcomes Qi and Ri, where the decision maker is indifferent. Okay, the two lotteries here are the same, except that we have Qi here, Ri here, but the decision maker will be indifferent. Again, because the decision maker only cares for final outcomes. Okay? And the last axiom, this is a technical axiom. This is about continuity. This axiom tells us that if we have three lotteries such that P is preferred over Q, which is preferred over R, then we can find some weight alpha such that we can construct a compound lottery of P and R such that the decision maker is indifferent between Q and this compound lottery of P and R. So this is a technical result. This ensures that there are no lotteries that are infinitely better or infinitely worse than other lotteries, because whenever we take a convex combination, we can approximate this by another lottery. You might have heard about the intermediate value theorem from analysis, where basically the idea is if you have a function with positive and a negative value, and this function is continuous, you will have a root in between, like somewhere where the function takes the value 0. And this is the equivalent formulation of this axiom, therefore it's also called continuous. Okay. Let me conclude with the von Neumann-Morgenstern theorem, which is the analog of the utility representation theorem, just for the risky environment. So the von Neumann-Morgenstern expected utility theorem says the following. So we have two statements which are equivalent. The first one is that the preferences satisfy all the four axioms we just mentioned: completeness, transitivity, continuity, and mixture monotonicity. A reduction and substitution axioms, so the two we had before and the four that we just had. If preferences satisfy all those 6 axioms, then these preferences can be represented by expected utility. And similarly, if preferences can be represented by expected utility, then the corresponding preference satisfies all of those 6 axioms. Okay? So, proving that if proving that the second statement implies the first statement is rather easy, I would say. And again, I would recommend you doing this as a homework exercise. The second one is a bit more complicated. I don't think I have time for this right now, but I've written it down and I will upload a note on the proof. And if you have any questions about that, or if you think it's too complicated, we can also discuss this at the beginning of the next section. Okay, thank you very much.
Something on the additional reading. This one, the information economics chapter 3, can I have something on this? I just didn't understand why the right structure is not finer than the left. I just didn't get that.
Okay, these are, okay, this is from the book. Okay. So the white structure,
Yeah.
What does finer mean? Finer means that when you have an original information structure, you only combine elements. And here in this case, this one is, here you have 5 and 6 together.
Yeah.
But actually about 6, this one, the left one, is more informative because it can distinguish between 6. So therefore, the right one is not finer than the left one.
I thought, I can still distinguish those four. So I thought it would be finer,
Yes, but it has, I see where you are coming from, but it has to be finer everywhere. So you're completely right. If for example, it would be 1 and 2 together,
Yeah.
but 5 and 6 separate, you're right. Then it would be finer than the left one. But you have to make sure that really any information that is in the right one is also, or any information that is in the left one is also in the right one. And this is not the case, because here you can tell, actually it's 6, but here you can't. So in that one thing it's less informative, therefore it's not overall.
Okay, that's why I have to check for everything. Okay, thank you.
Excuse me?
I just want to reconfirm.
So I
Geographic. So, have you made any change from the syllabus compared to last year?
Okay, so I plan to use similar material, but I don't know how progress at the same speed. I might add additional material for my distance material. I have to see how fast I do. In general, I plan to do similar, but also apply to my own material, like my own slides, so I cannot upload all the material.
Oh, yeah. Yes.
I plan to, for the future, I plan to upload the slides earlier on the weekend so that you have some time to
Read it.
prepare. Yes.
Yeah, but from
And the notes I will always upload after the lecture. This is just because there are some exercises that I want to do in the lecture that, yeah, if you before then you don't
I think this lecture and the lecture from last week are quite similar to the past years.
Yes,
Similar.
the lecture.
Oh, okay. My second question is actually usually in Manchester, we have for a 2-hour lecture, we have 5 minutes to 2 minutes break in the middle.
Okay.
For students to use quietly.
Okay.
Because you didn't do the last time also for this time, so just
Okay.
kindly
I don't know.
remind.
Okay.
Okay.
No, I'm happy to do that.
Okay, sure.
That would mean that the lecture takes longer, but okay, I'm happy.
Cool.
Then I will change it. So 5 to 10 minutes.
Yeah, about in the middle.
Okay.
Hi, Professor. If we have the test, the final exam on campus, can we maybe bring a paper, like a cheat sheet to the exam, or just?
I haven't decided that yet. Typically, I think that's not necessary because we don't have that many. So we have a few juniors, but if you understand the
Yeah, but for like some, just like you say, that some proof is quite similar to the proof in the lecture. So this kind of proof, so how to prepare for this proof because it's quite long and quite complex.
That is true. So first of all, practice is the best advice because I know now it looks all very intimidating, but if you really go through it and if you do maybe a second or a third proof, 3 or 4 times a month, you will train more proofs on the problem set, and then this is the hardest version of what you see. On the next time, it will be always easier. So
That's why it's an increase assignment.
Second member, thank you.
I actually got a suggestion for the lecture. So I found that between each concept there isn't too much of a link. Like, is it okay next time if when you teach, can you use linkage between the concept? Like for instance, like say, this is what we done, like using one word to summarize the last concept, and then to build a bridge between the last concept and the second concept, so we know why do we need this, and what does it used for, and how we're gonna do it. Can
no,
we do it next
of
time?
course, I'm happy to do that, and
Yeah,
also
thank
it will be more easier from the next lecture because the first one was kind of an introduction. We did a lot of like this probability calculations. All this will appear again, so this was an introduction, but now thank you for the help.
Okay, thank you.
I have a question about the tutorial. So, in the email you said it was in week 4. Will we have tutors in week 3? So, next week or
Week 4 is next week. Right now it's week 3. Week 4 is next week. So next week there will be a tutorial. And it should also be updated on the timetable. No, I think there was an issue before, but they should have fixed it.
Just one question. From last week, if A is finer than B, does that mean that you can make that A is a subset of B?
A is finer than B, then any subset of A is any set in A is a subset of a set of B, and no set in B is a subset of set in A, a strict subset.
So that means if A is finer than B,
are being chopped into more less pieces. Like, for instance, before we have 1, 2, 3, 4, 5, 6.